Welcome everyone to this session on Cirq. So for those who don't know, Cirq is Google's programming library for quantum computing, similar to Qiskit by IBM. And today we're just going to have a quick introductory session. We're going to have a look at Cirq, how it works, go through some of its basics. And it's all basically content that you've already learned throughout the main WOMANIUM talks, especially the ones by QWorld and by Gibran. So yeah, hopefully it shouldn't be too difficult, but of course, let me know if there's any concepts that need revising or anything that isn't clear, just feel free to chime in at any time. So I've sent the Google Colab notebook in the chat. I encourage all of you guys to follow along with me. Just make copies of the notebook on your own Google Drives and feel free to follow along. And with that said, let's get started then. So Cirq, what's it about, and how does it differ from Qiskit by IBM? Well, I like to think of it as a more device-specific programming language for quantum computing. So Qiskit, it really prides itself on working with various vendors, partners, and being quite hardware agnostic, I would say. So what that means is it's pretty independent from the hardware. You don't necessarily need to know what exactly you're running your software on. Since it has functions that does all of that for you. So if you're running your code on a specific IBM quantum computer, it transpiles or converts your code into a format that that specific device will understand. And many other features like this, which basically make it quite a general programming language to use. You don't have to think much about the architecture and the hardware that you're actually running your program on. Now with Cirq, that is not really the case. Cirq is specifically made for these hardware-specific use cases, and I believe it mainly supports Google's own quantum computers. So it has a lot of different extra tools that you may not have used in Qiskit if you're a beginner, and we'll see what some of those tools are today in Cirq. So to get started with, Cirq is a Python framework that's created by Google and is used to write quantum programs. It's made for the NISQ era of quantum computers, or noisy intermediate scale quantum computers. So these devices usually, they have about 100 qubits and they can execute around 1,000 gates without decohering. So there's this concept in quantum computing, for those who don't know, called circuit depth, which is basically the amount of sequential executions you can do on a specific qubit. And usually that limit is about 1,000 gates in our current era of noisy intermediate scale quantum computers, or NISQ devices. So more than 1,000 gates, you'll have your qubits decohere, they'll lose their results, they will lose their quantum effects. And so it isn't desirable, right? So we try to keep the depth of our circuits as low as possible, usually at about 100 or so, and that only for machine learning applications or things that have a very large circuit depth. And then about 100 qubits. Now, Osprey, IBM's recent computer, does have about 433 qubits, I believe. But then again, not all qubits are made perfectly. Some of them have higher error rates than others, as well as other specialties, pros and cons. So those need to be taken into consideration. And that is really what Cirq is all about, taking these device nuances into consideration while programming. So with that said, let's get started with preparation. So we're going to be using Cirq version 1.1.0. This is a bit of an old version, but then again, this notebook is also pretty old, actually. I had to sort of change a lot of stuff here and there to actually get it working. So we'll just stick with this specific version. It doesn't really change too much. So first thing we'll do is install it using pip. And then here is an image of the Sycamore chip by Google. So this is a very, very popular quantum chip. If you've been following quantum news over the past year or two, this is actually I believe is the first quantum chip ever that actually was able to do something faster than a classical computer or achieve quantum advantage. And Google made a whole series of videos and research publications about that. And it was done using this exact same chip, the Sycamore. So what we're going to do is we're going to import these libraries here and then have a look at this. So you call this a qubit mapping or coupling map. This is basically all of the qubits that are in the Sycamore chip and how they're connected to each other. So I said that we'd be looking at the specifics of the device, and this is an example of that being done over here. So what we basically have is different columns. So the second number that you see here are the columns. So this is column 0, which has only 1 qubit, column 1, which has 3 qubits, column 2, which has 5 qubits, and so on. So you have 9, or it starts from 0, so 10 columns in total. And then for each column, you can see you have a different number of qubits, right? So over here you have, so it starts sort of top to bottom. So you start with the qubits at the top in the first row. Those are sort of the 0th qubits. Then you have the second row, which are the first qubits. You have the third row, the second qubits, and so on. And you can see that there are also 10 rows of qubits in this device. So you have 10 rows of qubits and 10 columns of qubits, and each of them have a different number, right? And you can also see what qubits are directly connected with each other. So when you're making something like a GNC circuit, which is basically when you have a Hadamard and then multiple CNOTs across all of the different qubits. So it's a fully entangled circuit across your quantum computer. The only states that you can get are either all zeros or all ones, depending on the number of qubits that you have. So implementing one of those states requires that you entangle all of your qubits together. And when you have a device like this and you're actually working with the device itself, it's very important to keep in mind how you would be running these sort of circuits or fully entangled circuits, because you can't necessarily connect each qubit with each other qubit directly. So if I want to connect this qubit here, so qubit 94, to qubit 05, for example, I can't just do that directly. You can see that there aren't any direct connections. So I'm going to have to sort of bypass it through all of the other qubits. So 9-4 will communicate with 8-4, which will communicate with 7-4, 6-4, 5-4, and so on, all the way up here until it reaches qubit 05. So this is a very important concept that you need to be aware of when you're working with quantum computers on this level. It's very much like working on assembly in normal classical computers. That's sort of how I like to think of it as. And these things need to be kept in consideration when you're working with these computers. So this line right here is the same one that we had over here. It just prints out the qubit mapping of the specific quantum device. So there are other devices. This is Google's Sycamore device. I'm not sure if this one is still active. They have another device called Foxtail. Yes, so this was an old device. I believe it's not supported in this version anymore. Well, anyways, this is the Sycamore qubit mapping, and there are many other devices that you can try as well, made by Cirq. But for now, we're just going to stick with the Sycamore device. Be aware that Cirq is still an alpha software, which is why things are subject to breaking all the time, including when I actually got this, my hands on this notebook for the first time. I had to change a lot of versions and stuff. So for stability, it's better that you just stick to a specific version, which is why we're using 1.1.0. So let's get started with some actual Cirq basics then. This seems a bit overwhelming, but we'll go through it one by one. And again, feel free to chime in at any time and ask questions. So Cirq works a bit differently than Qiskit. It doesn't necessarily have just like, your qubit structure and then your circuit depth, so your gates one by one. It's a bit more detailed than that. So in Cirq, you have essentially 3 main components that you can work with, or you could even say 4. The first is a circuit. So this is your quantum circuit, much like you have in Qiskit. So this entire image that you can see over here is your quantum circuit. Inside each circuit, you have a collection of moments. Moments are essentially gates or operations that are executed in the same exact time frame. Hence, you call it a moment of time. So assuming that, just for example's sake, each column that you can see over here is 1 second. It has a period of 1 second. So it would take 1 second to run all of these different computations that you see here. And they're being run sort of in parallel across multiple qubits. Some of them might even be, 2 qubit gates or entangling gates. That's fine. But whatever gates you have in this specific column are going to be run in that exact time frame. So this is very, very important when you talk about concepts like DD or dynamic decoupling, I believe the full form was. So dynamic decoupling is actually an error mitigation technique that's used to reduce errors of your quantum computers. And the way it does it is if you leave your qubits in superposition or entanglement, but you don't do any active operations on them for a long time, they're just going to automatically decohere. So you need to sort of consistently keep them working, even if you aren't doing operations at that moment in time. And so you need to put unitary operations that basically don't change the actual content of your circuit, but it just keeps the qubits busy. So those can be like 2x gates in sequence, and so it just comes back to, where it started from. It can be a series of identity gates and many other things as well. So these sort of things are very important when you talk about moments. Moments are how we implement these sort of things, right? We need to execute these X gates in a specific time frame. So how do we know what time frame we're executing them in? We can use moments for that. So moments, what do they have inside of them? Well, they're a collection of operations that act during the same abstract time slice, right? In each moment, basically. So these operations are basically your quantum gates. They are a specific quantum gate that you're running on the qubit at a specific time. And you can have multiple of those operations or gates running on multiple qubits in the same time frame or moment. So the most common type of operation is a gate. There are other kinds of operations that Cirq has, and again, the reason for that is because it's so low level. But we'll just be sticking to the gate class for this session. And when you apply a gate to a specific qubit, you're applying a gate operation. And hopefully this diagram should help simplify all of these different things more. So this is your circuit. You have these individual columns. These are your moments. Inside each moment, you have your operations, which are these blocks. So each of these blocks is a particular operation. And those operations are usually gates or gate operations that you are applying on your circuit as a whole. All right. So let's actually start doing some stuff practically then. So let's try creating a circuit inside of Cirq. So in the previous cell, we imported Cirq, so hopefully everything should be working fine. So let me just run this cell, and then I'll explain sort of what this code does. The first thing you notice over here is, this weird diagram right here. It looks pretty similar to Qiskit's draw function, without matplotlib, of course. This is just basic text or latex. It looks pretty similar, actually. So that is actually what this is. This is an implementation of, well, it's similar to Qiskit's draw function, but it only displays in latex. As far as I know, there is no way to display this using matplotlib, or at least without some custom coding. So this is sort of what you have to deal with Cirq. You don't have that beautiful matplotlib plotting. You're just going to have to work with this latex plotting instead. So what does this code actually do? Let's sort of have a look at this right here. We try and zoom in. So first of all, we have variable A, variable C, and variable B and variable C. So A, B, C, these are my 3 qubits that I'm using inside my circuit. So just like how you have quantum registers inside Qiskit, these are basically sets of individual qubits that you have, and you are executing operations on these individual qubits. So here you have qubit A, qubit B, and qubit C. We are using a method called named qubit, which is just used to give them a particular name. So in Qiskit, you usually have a default naming convention of Q0, Q1, Q2, and so on. But there is a method where you can actually name them to anything that you want. And that's what we're doing over here. We're just changing the name of these qubits to A, B, and C. After that, we're applying operations on this circuit and these qubits. So how are we doing that exactly? Well, you can see that the qubits are actually independent from the circuit right now. So we haven't really binded them to a circuit yet. And that's exactly what we'll do with the operations as well. We'll execute them sort of individually, and then we will apply both the qubits and the operations on the circuit together. So here in this operations list, this is a list of all of your operations. And over here, we're specifying the operations that we want to run. So here we have cirq.ha. You may find this familiar to the Hadamard operation in Qiskit. Is the exact same thing. So here we're executing the Hadamard operation on qubit A. You can see this in this latex output as well. We're executing the edge gate on circuit B. That's also being done over here. After that, we're executing the C0 operation on qubits B and C. And you can see that it shifted to the next column, right? So it's now in a different column. So this is essentially how Cirq looks at moments and how it works through them. When you have repetitions of specific qubit names, it automatically moves to the next column. So you can see over here, we've called on B twice. So cirq.hb, so that's our first gate. And then we're using the C naught gate. So the control is qubit B, which is why it's shifted to the next column. So since we've called on B the second time, it's now shifted to the second column. And you can see this weird sign over here. This is just the at symbol. And this is what specifies the control. And then we have this line, which is indicating the joint qubit, the 2-qubit operation. And then this is our X gate, right? The NOT operation that's executed on qubit number C. And what's also interesting over here is when you have multi-qubit operations or the C naught gate, for example, a 2-qubit gate, the target is also on the same line as the control. So it's in the same moment, it's in the same column, so it'll be executed at the same time. So I want you to look at these different columns that you see in Qiskit and Cirq, because the theoretical concept is the same, as moments, as specific slices of time where these operations are being executed. And that makes it much easier to sort of understand what's going on here as a whole. And yeah, finally, we have this fourth operation. This is another edge gate on the qubit B, which you can see over here. And CX is just C naught, right? So C naught or CX, the terms are interchangeable. In Cirq, you just use the term C naught because I believe CX does not exist, but you can try. Oh, okay, so CX also works. You can use both of them, CX or C naught. It's really up to you. Here we have, so this is sort of where we bind everything together, right? We have our 3 qubits and we have our operations. Now, how do we bind them together? Well, here we're just creating a generic variable called circuit. And here we are calling upon the circuit method, which creates a circuit using a specific set of operations. So you don't need to specify the qubits because it automatically takes into account the qubits that are used in the operations. So over here we have qubits A, B, and C, and hence it automatically sort of prints out the operations for A, B, and C. Now this is interesting. Let's say I wish to remove this part. So what I'll do is I'll just copy this line here. I'll comment this out, and I'll remove this C naught. I'll remove this C naught from this list. So now qubit C, this third one, is not being used in the circuit at all. So if I execute it, you will see that qubit C does not appear because we're not using it. So since we didn't specify qubit C in our operations list, we are doing an operation using qubit C, it's just going to be ignored. So our circuit is not going to have any showings of qubit C because we aren't applying any operations. So it's just going to be blank. This is not like Qiskit, however, because in Qiskit, you sort of put all of the qubits into your circuit, even if they're blank, and then you just execute operations on the qubits that you want to, right? So over here, it's just a bit different. So whatever qubits you apply your operations onto, those are the ones that are going to be shown in your circuit. And then this is the exact circuit that actually gets sent or transpiled to your actual hardware. So it sort of makes it easier to see what exactly is going on in your circuit. So if you have like 1,000 qubit machine, you don't need to scroll through all 1,000 of your qubits in Qiskit to be able to see what your where your actual circuit is being executed on. It's just the ones that are being used. So that's something good to know. I will move this line, revert it back to this one. There you go. So we have another concept over here called grid qubit. So we already know what named qubit does. It creates a qubit with a specific name. But what we also have is grid qubit. So if we are creating a circuit for a specific device like Bristle phone, it's another one of Google's devices, we refer to 50 as the qubit at the top leftmost position of the device. So if we go back over here, we'll see what I'm referring to. So it says top leftmost, right? And sorry, the leftmost position, not top leftmost, just the leftmost position. And you can see that's exactly where this is, right? So even in the Sycamore device, 50 is the one that's leftmost. So you use these sort of referencing methods for the positions of the qubits inside your coupling map. And you can do the same thing for creating a grid qubit. So if you want to put or do something with a qubit that's in a specific grid, and so it's already part of a bigger structure of a quantum computer, like, you know, a Bristle device or a Sycamore device, then you can just refer to that specifically. And so we already know how named qubit works. We know that Cirq.h is the Hadamard gate, and here's the mathematical representation of the Hadamard gate. So 1 over square root 2 times this unitary matrix right here, 1, 1, 1, and -1. And then this is really where your phase kicks in. And the gate objects have the ability to be applied on one or more qubits. So there are two ways to do this, really. You can either use the ON method, or you can just directly call the gate, right, as if it were a function. So you can either do this where you're like cirq.h.on A, as in I want to apply my H gate on qubit A, or I can just call on qubit A directly. It just depends on how verbose you want to be with this. The result of these expressions is a gate operation, which is the operation that you're applying inside your circuit. And there is a strong distinction between operations and gates. That is quite important. We won't be working too much with that here in particular, but either way, the differentiation is important. So an operation is associated with a specific qubit and can be put inside a circuit, while a gate does not have a specific qubit, so it has unspecified qubits, and will only produce an operation when given some qubits. So what we just did above in this operations list that you can see over here, so this was using operations because we're associating with this with a specific qubit. So cirq.h is actually an operation. And then if we talk about gates, gates are a bit different, and we'll see what those are in a bit closer to the end. And gates themselves are just generic. You can apply them on any qubit, and it will give you an operation that will sort of be applied on qubits. So like a repetitive function that you can use. Any tips for the max cut Grover exercises? We can maybe talk about those later if we have some extra time. But for now, we'll try to focus on the Cirq section as it is. I'll be happy to answer questions on Discord. So you can just PM me or tag me on one of the channels, and I'll be glad to help you guys out. But anyways, once you have a collection of operations, you can then construct a circuit like this. More so on this in a minute, but it's basically circuit, and then you specify the operations, which is exactly what we did over here as well. So Cirq has a ton of different gates, like there are a lot of them. And here I just created a massive operations list of all of the main ones that you need to know about. And there are a lot of these that you may not have used so far. So like the T gate, the S gate, or maybe the Y gate, and many others as well, like the C swap gate, or even CCX gate, or Toffoli gate, I swap gate. So all of these are different gates that you can apply in your circuits. And I believe Qiskit has all of these circuits as well, or at least specific implementations of them. Maybe they have a different name. And these are different operations that you can use inside Cirq in your circuits. So I just want to point towards this specific syntax here. So this is cirq.line qubit. And here we're just specifying a range. Basically, what we're doing over here is we're creating 3 qubits in a line. So this is just, I believe there's a name for this as well. Destructuring, I believe, or something similar, where you basically have, like, you can destructure a list. So if you have a list with 3 elements and you put 3 variable names on the left side, each variable will be assigned to each element inside the list. So similarly, we have a list of 3 qubits, a range of 3, and we're assigning the qubits to each variable that we have over here. So Q0 is the 0th qubit, Q1 is the first qubit, Q2 is the second qubit, and so on. So range 3 means 0, 1, and 2. This is the terminating point. So there's no qubit 3, it's just qubit 0, 1, and 2. So this is non-inclusive. All right. So the last thing we did in the example code was, surprisingly useful, the ability to actually print the circuit as a text diagram. And it's visually very helpful, but it doesn't really get the internal details of how the circuit is actually being represented. Because it's made up of these individual moment objects, right? We talked about this. And if you want to have an idea of how each moment actually works in the circuit and what each moment is doing in terms of operations, it's important to iterate over the internal structure and have a look at what's actually going on. So here are 2 ways that you can actually do this. One of them is, well, this one, as you can see, is a lot more sort of formatted, or you could say it's a pretty print of this internal moment structure of the circuit. And then over here, this is just the more generic structure, or you could say it's less readable, right? So over here, how do you actually go about reading this in particular? Well, over here you have the moment index of moment 0, 1, and 2. For each moment, you have the qubits that are being used. So in this case, qubit A and B. What I'll actually do is, so we can see this easier, I'll copy this code and I'll just bring it down in new cell. So we can sort of just compare these against each other. So code, and there we go. So over here, we are doing an etch operation on qubit A and an etch operation on qubit B. Both of these are being executed in the same moment, which is why you can see both of them in moment 0. And what are we doing? We're executing the etch gate. So you can see that we're executing the etch gate on qubit A and the etch gate on qubit B. So that's the first moment. On the second moment, we have the CX gate. So in the CX gate, we're using qubits B and C, and we're using the B as a control and the C as a target. And hence you can see this is the control, the @ symbol. This is the thing that's joining the control and the target together. And then this is the target itself, or the X gate, that's being implemented on qubit C. And then we have the final moment, moment number 2, which is just an etch gate on qubit B, which you can also see over here. So it's pretty easy to read in this particular format. This one is a bit harder. So again, I'll just move this down. So with this specific one, you can see it's basically a list of, well, tuples of tuples, basically. And in each tuple, we have the index of the moment, so 0, 1, and 2. And then we have the actual code that's being used by Cirq to actually reference all of these. So instead of just giving us a nice visualization of this, is just sort of spitting out the code right in our faces. So we have Cirq.moment. So this is the entirety of the moment. And then in this moment, we have these 2 gates. And then this is basically just the same thing that we've implemented here, although instead of using the variable A, this is just an extraction for us, it directly specifies Cirq.name qubit A, which is why you can see that it's a bit longer. The output's a bit longer over here. And then you can just sort of copy paste the same analogy for the first moment and the second moment. So we have the C0 gate here and the etch gate over here. The pi latex ink error, so you might be getting that both in Cirq and also in Qiskit. So I'll just go through that real quick. In case you're getting this error, just do this. So pip3 install pi latex ink. This is the library that you usually use to display stuff in latex. And you're probably getting this problem in Qiskit, but it's possible you'll also be getting this in Cirq. So once you run this code and it's executed successfully, make sure that you restart your kernel, because you don't need to import it yourself. Qiskit already uses it as a dependency. So just make sure that you install it, restart your kernel, and then it should be working properly. If it doesn't, then you could try manually importing pi latex ink, and hopefully that should work after you do that. But that's usually to the extent that I've had the problem personally. You just download the pip package and then you import it, and it should be working after that. All right, next we have the REPR function, which is basically another way to visualize all of these different moments. And this one is basically very similar to this moment format, except you have lists inside of the tuples, and it's basically an entire hierarchy of your circuit, which you aren't able to see while you're actually coding. So Cirq.circuit, inside your circuit, you have these 3 moments. Inside each moment, you're implementing these gates, and then these are the qubits you're using for each gate. So you can visualize that even better. So yeah, that's quite a lot of different methods for viewing your moments. But again, this is an integral part of Cirq. You're using these moments to visualize the exact gates that you're executing at each time frame. And that's very important when you're talking about some specialized algorithms that you want to execute or specialized use cases. Like I mentioned, dynamic decoupling for error mitigation or others as well, where that time, the time frame or that moment really matters. So the usefulness of printing REPR is that it includes all of the gory details, right? And they can be useful when debugging. It's also a valid Python expression that evaluates to the circuit. So I believe you can use assert as well if you want to. So there's another sort of similar concept to this, which we'll see a bit further on, which is related to generators and iterating. But we'll see that once we get to it. We only have about half an hour left, so I need to go a bit more quicker. So above we created the circuit, but there are actually many ways to create all of these circuits and modify them in different ways. So here you're just creating the regular circuit, right? So you have the circuit class and then the operations inside of it. You can also use the append method because circuits are mutable. You can start with an empty circuit like this, and then you can simply just append operations to add on more and more operations if you want to. We also have insert, where you can basically do the same thing as append, except you just specify the exact moment that you want to put your that you want to put your operations inside, and that's just specified by your integer index, same as the moments. And finally, you can use a circuits constructor, which takes the list of moments explicitly, and then in each moment you specify the list of operations that you want to execute. And obviously, this is a lot more tedious, but it gives you complete control over how the operations are laid out. So, you know how sometimes there's this annoying thing where, especially in like GHZ circuits or like entangled circuits, that, you know, sometimes the gates don't display in the exact moment that you want them to, or you want them to be in another moment, but they just don't work like that. So usually what you do in Qiskit is you have to use barriers and identity gates and, you know, all of that stuff just to align it properly. Well, in Cirq, all you need to do is just specify the exact moment that you want it in. And unless it's like a 2-qubit gate, where it's like illegal to basically have the control in one moment and the target in another moment, unless it's something like that, you should be able to do, you know, specify this exact moment that you want to execute your gate on if it's a single qubit gate. So that is pretty useful. So you may have noticed that there's sort of a bit of a hole in what we explained so far. You know, circuit ops, if you actually try and use this practically with different inputs, it effectively takes just a one-dimensional sequence of operations. But the output is a list of operations, and you can visualize that much better over here once you actually print these out. Not sure which visualization is talking about specifically. This is a single list. That's odd. Well, either way, there's a degree of freedom that actually hasn't been accounted for, which is how Cirq chooses the moment that each operation will be placed within. So basically, you can put individual lists sort of surrounding each particular operation that basically isolates their moments, sort of like this. And I'll encourage you guys to experiment more with that. But again, kind of running out of time here. You can basically surround individual operations with a list inside of a list to put them in a specific moment. So that's another way that you can do this if you want to, right? So we talked about inserting, right? Inserting in the middle of a specific moment location. So you can use these 4 insertion strategies. So you have earliest, which is the default, which is basically the absolute next one. You have insert strategy new, which I believe is your latest qubit or the newest one, the last one, or you want to interpret that. You have inline, and you also have new then inline. So earliest just scans backwards from the insert location until you find the one that you need. And you have new inline, which adds a new moment at the insertion point that I believe you specify yourself. You also have new then inline, which is it says the second most important strategy, which is basically, so instead of adding it to the direct new moment that you specify, it adds it to the one that is after it. So new then inline inserts it 1 qubit after the moment that you specify, basically. So that covers new, earliest, inline, and then inline. Perfect. So those are the 4 sort of inserting methods that you have. And I know this was a bit of a dry section of the notebook itself, but again, a big advantage that Cirq actually gives you in quantum computing is these different constructs to be able to execute these things. So that is quite important. But now that we learned about all of the sort of the gory details, the theory details, now it's time to actually do some more practical stuff and actually create some circuits using Cirq. So here we have a quick exercise, and should have minimized this. So this is an exercise to validate your understanding. Create, using the least number of appends possible, the following circuit that you can see over here. And before we go any further, I just want to mention that this gate over here, so you can see there's an at and an at. So this is the CZ gate, right? Control Z gate. And the exercise here is to try and create this specific circuit yourself in a new code cell. So what I'll do is I'll just pause for 5 minutes while you guys can maybe try and do this. And in the meantime, if anyone has any questions, then I'll be glad to catch that up. So yes, the moments are divided according to not the type of the operator specifically, but rather the when the operator is actually executed. So going back to this particular example, you can see that we're executing the H gate on qubit B, and then we're executing the C naught gate on qubit B and C. So this is the second time in this entire circuit where we've actually called upon qubit B. So each time you call upon a specific qubit for a different operation, it changes the moment automatically. That's sort of the default way of how it works. The default insertion, which is earliest, right? That is how it works. So it's not divided according to the type of operation, but rather the number of times you use each qubit for a different operation. Hope that makes sense. So for those who joined late, here is the notebook for you guys to use. It's in the chat. And what I'll do is I'll paste this on Discord as well. There we go. The link should be available on the networking channel. So we'll just wait for about 3-4 more minutes. And in the meantime, if anyone has any questions, then feel free to ask. Otherwise, try and do this exercise. It's a pretty fun one, and hopefully should get you up to speed with the basics of Cirq. So for a pen, does it work if we add a new qubit that wasn't on the list of operations? So a new qubit. So let's say you have this operation list right here. So if I try and specify an operation with a qubit that is not created, so it's not there, like over here, I've created these individual qubits, right? It's like creating a quantum resistor. I cannot use an operation on a qubit that doesn't exist. Yes. So if I try and add, let's say a Cirq, an etch operation, I'll just move this aside, an etch operation on qubit D, which doesn't exist, right? It's not there. And if I try executing this, it's going to give me an error. D is not defined. So yes, you cannot execute an operation on a qubit that does not exist. And it doesn't need to be part of your circuit. Remember, the only qubits that are part of your circuit are the ones that you specify in your operations list. I can have many more qubits over here. So like, just copy this syntax. I can have a qubit D, qubit E, qubit F. I can have all of these different qubits like so. And it's not going to make a difference on this circuit that I have over here. And the reason is because I haven't used it in my operations list. See, it's just exactly the same. So you can have blank qubits. Instead of quantum resistors, you're working with individual qubits. And I believe you can also have like a grid of qubits if you're working with a specific qubit layout of a specific device. So yeah, if you have extra qubits, it's not going to make a difference unless you specify them in your operation circuit. So if I do like Cirq H D, you can see that we now have a new qubit in my operations list. And another question would be, what if I have the same names, right? Because we are creating qubits that have specific names. So if I try to create another qubit D, another qubit called C that is assigned to the variable D like this, then you can see once it runs, it doesn't give any errors either. So this is basically just a label. And this label is really only used for your understanding as the user. So it doesn't really make a difference. And if I use this, for example, so circ.hd, you can see that the label that's going to be displayed on here is also C, and it didn't create a new qubit. So when you have, so this is basically like a shallow reference, you could call it. So since you have the same label, Cirq knows that you have different variables, but you're just referring to the same qubit. So when you do this operation on the qubit D, it just does it on qubit C anyways, because it knows that you're being stupid. So yeah, you can either create two or multiple references of the same qubit, or you just don't have the qubit at all. You can just remove your reference. All right, hopefully that should have been enough time for you guys to have tried this particular exercise. So let's have a look at the solution here. So this is the solution. You can see it looks, oh, I forgot the edge gate. Sorry about that. So this is almost exactly the same of what's in the circuit over here. I just forgot the edge gate on qubit C. Let me fix that real quick. So circ.h on qubit C. There we go. So here we have our CZ gate, right? So I mentioned this was the CZ gate. So you can use the word CZ. I don't believe there's a longer form. So like for CX, you can use either CX or C naught, right? So it's basically the same thing. You can do circ.cx or circ.c naught, it doesn't matter. But for CZ, I believe it's just this, it's just CZ. So this is your CZ gate. Here you have your H gate on qubit C. So you can see that these specific operations are on the same moment, right? The same column. Then you have, sorry, my camera was off. Hello. Here we have the edge gate on qubit A. So this is in a new moment, a new vertical column. Then we have, so that is all we've done for our main circuit. After that, we're just appending stuff, right? So we're appending more operations to our circuit. You don't need to do this. This is just for a demonstration. This is essentially how append works. And we talked about the insertion strategies, right? So I've specified one of those over here. I've used new then inline. And if I remove this insertion strategy, what's going to happen? Well, just give a demo of that real quick. It's not going to display in the same way. You can see that the qubits are now all sort of together, right? So they aren't being done on separate moments. They're sort of combining moments together. But the way that it's set up with new then inline is you're going to have this extra space, as you can see, between the edge gate operations. So you're not necessarily going to have this circ.ha and circ.hb in the same moment. Rather, you're going to have them on different moments. So that is what new then inline does. And all right, let's move on to, I believe this is the simulation part. So now that you know how to actually make a circuit, how about simulations, right? I mentioned that we would talk about generators real quick, and this is exactly where that is. So recall that Python generators, if you know how they work, they're basically iterators that you can use to go over a specific set of values. So we won't talk about much how generators work, assuming that you know how it works. This is a generator where we're just creating two edge gates and we're measuring both of these edge gates. So to measure inside Cirq, you use the dot measure method, and then you can specify the variables that you want to measure on. So in this particular case, you can see that there's a line that's sort of joined between the two. That doesn't mean anything per se. It's just how in Qiskit you have the measure all function, and you also have dot measure where you can specify like a list, right? So like I want to measure qubit 0, 1, and 2 to classical bits 0, 1, and 2. So that's basically what this is. This 0, 1, and 2 is just saying that, hey, these are all sort of measurement that I have inside my circuit. And so I'm just linking them together to make it easier to read. So measurements in this case are also done in the same moment, yes. And there are a few things to note here. We have this Python generator, and we're creating this this generator with this specific function. So we see that we can iterate over this basic circuit function, right? So that's what all of this code is inside. We see that when we do this, each yield produces what was yielded, which are the operations or list of operations. But when we pass this iterator to the append method, something magical happens. It's able to automatically flatten all of our operations and pass them into append, and it also works the same for insert. And the idea here is to use what's called an op tree. Basically, it flattens your circuit into making a very nice small pattern, which can vary by size, but the ideal goal is to reduce the number of moments that you have to decrease the circuit depth. So this is just basically one way to visualize what we visualized from before, where you can have these operations in different moments or different vertical columns. And each column means that your circuit depth increases by 1. So again, the more circuit depth you have, the higher chance you have of your circuit decohering, or your qubits decohering, meaning that they lose their quantum properties or you have some sort of errors. And to reduce that, you need your circuits to be as efficient as possible, as you could say, as compact together as possible, using the least number of moments. And so that is why generators, iterators, and generally how Cirq works, it aims to compress your circuit to the least amount of moments possible. But anyways, that was just a small tidbit. So here we have our main simulation. We're just creating a Cirq simulator. This is really nothing special. It's just a simulator. They do have other kinds of simulators, and I'll be glad to share some links at the end. These are cloud simulators by Cirq, actually, that you can activate right here on Colab. But it's not part of this particular notebook. Feel free to experiment with them later. So we're just using the regular simulator. We don't have like a Qasim simulator and state vector simulator inside Cirq, or at least not by default. So we're just going to be using simulator. We're creating our circuit, and the circuit is going to call the basic circuit function. So basically, this is going to be our circuit that we're going to be simulating. Here we are running our circuit, and this is actually just one shot. So in Qiskit, the default is 1024. Right now, we're just using one single shot, and I'll show you how you can use more shots if you want to. So you just call simulator.run, and that's it. You can just call your circuit, you can run it, and you'll get your measurement results like so. So what have we done in the circuit? Well, we have 2 Hadamard gates, and now we're measuring them. So the measurement results of each Hadamard gate individually will just be a 50-50, right? So you have a 50% chance of getting a 0 and a 50% chance of getting a 1 for each qubit. So here we have 1, and here we have 0. So you can see that unlike Qiskit, you don't have to think about the whole big endian, little endian ordering, because it outright tells you, which qubits these are in particular. So qubit A is 1, qubit B is a 0. And since it's a 50-50 probability, I can run it multiple times, and you can see I'll get different results. Now I'm getting 0, 1, now I'm getting 0, 0, now I'm getting 1, 0, and so on. So short means, yes, how many times it runs on the simulator or how many times it's executed. So quantum operations are probabilistic, meaning that the results really do depend on the number of times that you execute it. When you talk about flipping a coin, for example, and getting a 50-50 result, that 50-50 result only happens mathematically or statistically when you flip it an infinite number of times, which is impossible. And so over here, it's basically the same thing. It's a 50-50 probability, but each time you run it or each shot that you run it for, you will get a specific result. So again, the results are different depending on how many times you run this again and again. So running this time multiple times should result in different measurement results, since the above is a superposition of all of the basis states in the system. So above we use the run method. These actually mimic these methods mimic the actual hardware, in that they don't give access to unphysical objects like the wave function. So it doesn't work like state vector. So you know that there's a state vector simulator or a unitary simulator, or these sort of simulators. It doesn't work like that. It doesn't actually give you access to the wave function or the things that you can't really observe. If one wants to get that wave function, then you have to use the simulate method. So the run method is used to get like a Qasim output, you can think of it as, while the simulate method can do these other things, right? It can output this wave function, your state vector, your unitary matrix, and all of that. So simulate is like a whole other set of methods or classes that you use for this sort of stuff. So here we have our wave function in complex numbers, and here we have it in Dirac notation as well, which is very nice actually. So you can just use .Dirac and it prints it out for you in Dirac. Very nice indeed. Could we apply probabilistic equations on Cirq? Yes, I just showed you an example of one. This is 2 Hadamard gates. And this is the output that we're getting, half probability for all of them, in probability amplitude. So like 0.25 for, wait, why is it displaying like this? I just realized actually, that is odd. Huh. That's odd. So obviously the total has to come up to one, right? Like a probability of one. So I'm not really sure why it says 0.5 here in particular. That's interesting. So a half probability of getting a 0 or a 1 for this first set of qubits, and a half probability of getting 1 0 or 1 1 for this second set of qubits. I believe that's what it's interpreted as, but the way it displays is a bit weird, right? You don't usually see this in probability amplitudes or normal probabilities even, for that matter. These are not amplitudes. They probably are amplitudes. So if I square, the problem is I'd expect this to be 0.707, right? Because that is the value that you usually get is like 0.707, I believe. And then if you square it, I think it was square it, you square it, you'll get that value of 0.5, and that will actually be your correct value, right? So yeah, anyways, it's still relatively understandable by the way that it's written over here, especially in direct notation. So that's not much of an issue. Notice that we passed a qubit order into the simulate method. This is very important. So we've ordered it by A and B. And this might actually be why the issue is. If I print this again without the order, so now it's okay. So this just changes the order itself. That's fine. So I can specify a specific order that I want to output it in. So I can do AB. So AB is this order that you see right here. So I want to output it in BA, which is the reverse order. It's going to output starting from sort of the other way, but the results themselves are going to be reversed. Since it's 0.5 for all of them, the results are again basically the same thing. So the qubit order does not matter in this particular circuit, hence I'll just keep it blank. And this order helps define the order of the Kronecker product. If you know what that is, it's the tensor thing. Don't think I can print it out on my keyboard, but it's the tensor product basically. And you can sort of sift between those Kronecker multiplications. Since again, we're just doing a simple Hadamard operation on both of the qubits, the Kronecker order does not matter. If we tensor A to B or B to A, doesn't matter, right? Because at the end of the day, an H and an H together will just give you this exact same result. The qubit order argument is optional. When it is omitted, the qubits are sorted in ascending order. Otherwise, you can sort it using multiple types of qubits. The name can also be used as a quote unquote tiebreaker. If you have the same number of operations or names like that we have over here, for example, both of the qubits have the Hadamard operation. So you can use the type of the qubit as a tiebreaker as well. And we saw one of these above, the line qubit, I believe was one of the examples. This one right here. So it depends on this. What else? So the simplest qubit order that you can provide is the list in which you want to order it in. Any qubits from the circuit that are not in the list will be ordered in default string ordering. After the qubits that are in the list, but they come after the qubits in the list. Sorry about that. And be aware that all of the qubits in the list are included inside the simulation itself, even if they're not operated on by the circuit. So remember how we said that the draw output displays it without actually, so even if we have more qubits but they don't have any operations, remember how we said that the simulator, the drawing output wouldn't care? Well, that's not the case with the simulator. The simulator will include all of the qubits even if they're not operated on by the circuit. So only in the draw output will you see this, where only the qubits that you're actually doing operations on are in the output, otherwise they just aren't. And the mapping, you can have a look at this using numpy.cron. We're not going to go through this in particular. All right, then we also have repetitions. I mentioned shots, right? So if you want multiple shots, you can use repetitions. In Qiskit, I believe it's shots equals, but over here is repetitions. So you can specify how many times you want to repeat it, and you can also get your output as a histogram. So basically exactly like the Qasim simulator, and you can specify your key. Your key in this case is the qubits that you want outputted in order. So over here, you can see we have 1, 3, 2, and 0. So 1 and 3 basically stand for 0 and 1 on the A qubit. So 0, I believe it's 0, 0, and 1, 0. So I'm talking about the qubit on the left, which is the A qubit. And then you have qubit 2 and qubit 0, which is 0, 1, and 1, 1. I'll actually write that down to make it more visual. So you have 0, 0, and 1, 0, and you have 0, 1, and 1, 1. So you can see over here, A qubit is common. Over here, you can see that the B qubit is common. So that's basically what this is doing over here. If I switch the order, it should display in the other way. No, sorry, extra space. BA, that's odd. It doesn't want to display in the opposite format. I believe it's because we executed it, or sorry, we made the circuit itself in such a way where you can't necessarily change the keys around. So again, the chronicle product must stay the same, even though in our case, it doesn't make a difference, which is exactly what we tested out. Where did we test this out? Yes, we tested it out over here with that extra argument, but we do not need that because again, it's just two H gates. But when you're actually printing the histogram, you're not allowed to change the chronicle product sequencing. So that's exactly what's going on over here. The histogram method can be given a fold func argument to group the measurement results under a specific key, and you can just use lambda functions and stuff. So I'll just give you a general idea of this, not going too deep into this. You can group your various results into something like this, agree or disagree, and you can see it has a 50-50-ish probability over here. Finally, matplotlib. Remember how I said that you can't visualize this normally? Well, you can, but you're just going to have to use matplotlib sort of yourself. Cirq does give you an implementation of histogram, so you can just call it directly from Cirq. You don't need an additional dependency. And if you're having problems over here, then just import PyLatex like I mentioned before, and you should be good to go. All right, we have 1 minute left. Final part before I'll let you guys leave is the quantum teleportation protocol. So just going over everything that we've learned so far to create this circuit. We're creating an empty circuit over here. We have 3 qubits, the message qubit that's going to encode the message, Alice's shared part of the entangled state, and then Bob's part of the shared entangled state. And if you don't know what I'm talking about, feel free to reference Gibran's lectures. I believe it was Q Bronze. Or you can have a look at the original paper on Wikipedia. The input gate prepares the message to send. So what we've actually done here is we've created a function that has this method called gate. Remember how I said that you can create gates or like functions that are separate from the qubit that's being used? So that's exactly what we have here. We've created a gate, which is basically just a version of the X gate, and it doesn't have a specific qubit that's specified. So you can specify that yourself inside this function over here. Or sorry, not inside the function, but rather on the qubit that you're executing in particular. So you can specify this gate, so cirq.x, and then over here, you're applying cirq.x to the message qubit. So this message is the qubit that we're using. This is called the message qubit. Do we have access to the site? No, you do have access. This is the Cirq notebook. Please check the networking section on the Discord platform, and you should find it over there. So on the networking channel. Okay, after that, we have cirq.append. So this is just the appending the message that we want to encode, which we're going to do over here in a bit, into our circuit. Then we are importing the H gate and the C0 gate to actually entangle Alice and Bob's qubits together. We are the entangled measurement of the message and Alice's entangled qubit. We are having a look at this over here. And then we're using the 2 classical bits from the entangled measurement to recover the original quantum message, right, on Bob's entangled qubit. So over here, we measure it, and then over here, we recover the original quantum message on Bob's side. So now that we've done all of this, this is sort of the main quantum teleportation protocol. Over here, we define the gate, the actual encoding, and then we'll be able to view that encoding. So we have multiple options over here that we can use. So the way we're going to do this is, let me just try doing it default first. So this is our entire circuit, and then this is our message qubit that we're encoding into the circuit, right? And let me just run all of these. So over here we have, so you can see this gate.on syntax. We talked about this. You could optionally remove this on syntax, but it's really up to you. You're specifying the message qubit, and we're getting the final state vector of that qubit, right? This is what's being displayed over here. And we also have the block vector from the state vector. We can get access to that as well. But I don't believe we are printing it out. Okay, so we're printing out the block vector itself, which is just in this format. Okay, so this is not the block sphere, which you may be used to. This is a block vector. The slight difference here is it still works according to the rotations that the block vector uses. So you're basically just transforming those values from the state vector to the block vector, but you can't actually see the sphere itself. So that's just a bit of the difference here. Awesome. Claudia, you're ready for the next session. I'll just be done after this last cell. Over here, we're simulating our teleportation protocol. And over here, you can see we have the state 0 and 1. If I change this to, let's say, x to the power 25, and again, these are just the actual mathematical rotations on the block sphere. Oh, sorry, 0.25. 0.25 right there. You can see that this is what's encoded over here. And once we run it again on the simulator, instead of the state 0, 1, we should be getting the state 1, 0. And you can mess around with these different rotation states to be able to get the specific qubit, the specific message that you want in the teleportation protocol. So the final state of Bob's qubit is always the same as the initial state of the message qubit that Alice sends. And you can change the gate above to really change what that message is that's being sent from Alice to Bob. And that is all that I have for today.